done now is we have spent roughly a third of the semester talking about integration techniques and becoming very good at finding antiderivatives for a ton of different functions. So what happens now in Chapter 7 is that we're going to apply all of that knowledge, and we're going to be talking about definite integrals and some applications of these definite integrals. So why the heck did we learn all these techniques? Well, the reason we learned all these techniques is so that now we can use integrals to answer some interesting questions. So section 7.1, the topic is area between curves. All right, so here's our first example. We have four equations. Y equals 10, y equals negative 3, x is equal to 2, and x is equal to 6. All right, so these are four equations, and these are equations of lines. And I can draw a picture of these four equations. So here is my x and y axes. Y equals 10 is somewhere up kind of high, so here's y equals 10. Y equals negative 3 is somewhere down below the x-axis. X is equal to 2 is a vertical line. And x equal to 6, also a vertical line. Okay, now there's a lot of white lines going on this chalkboard, and I want to make you want to make sure that you're not confusing the y-axis and the x-axis with the actual lines that we're interested in. And so when I look at these four equations that I draw the picture, here's a question that we might ask. We might ask the question, find the area bounded by these lines. So the first thing that I might do is pretend like I'm in kindergarten and try to color in this region. And so the region that we're looking at is the area that is below y equals 10. So below y equals 10, above y equals negative 3, and between x equals 3 and x equals 6. And so there it is. That's the rectangular region we're looking at. Okay, so take a look at that region. And I would like for you to say hello to your neighbor. And I would like for you and your neighbor to discuss how you're going to find the area of that region. 52, and we're talking about units, so square units, whether it's square centimeters, square inches. I didn't define that, so we'll just talk about square units. Okay, Bradley, can you talk a little bit about where that number came from? How did you come up with that?
Well, we just looked at the shaded area just as a rectangle.
Okay.
The area of the rectangle is length times width. Or height, base times height.
Okay, so length times width, and so when you look at the area of a rectangle, and we've got length times width, so here our width looks like a width of 4. So our width ended up being 6 minus 2, which is 4. And this length here, well, we've got from 10 down to 0, plus an additional 3 onto the bottom here for a total of 13. Okay. So we've got 13 times 4, which is 52 square units. Any question about that? Okay. All right, so just as an observation, and this is sort of a silly observation, but I just want to observe this. This 4 was pretty straightforward to calculate in terms of, okay, we're going from 2 to 6, so 6 minus 2 gives us a distance of 4. This height here had a y value that was negative down here, and so one way to think about this height is that we've got 10 units above the x-axis as well as 3 units below the x-axis. But alternatively, we can think about this 13 as 10 minus the negative 3. So we can think of the height of this rectangle as top minus bottom. Okay, so this is a totally valid way to come up with the area of this rectangle. We know that the area of a rectangle is length times width, or base times height, however you want to think about it. And since this is definitely a rectangle, then we can calculate the area using those values. Okay. So I'd like to remind you, since we haven't really been talking a whole lot about this semester, is the entire point of integrals, so far anyway, when you talked about them in Calc 1, the purpose of definite integrals was to talk about the area under a function y equals f of x, starting at an x value of a and ending at an x value of b. And we were interested in finding the area under that function and above the x-axis. Now, what you may or may not recall is that in order to find this area, because that function on the top is curvy and not just a nice rectangle, what we had to do was to take this region and break it up into rectangles. And so we broke this up into really tall, skinny rectangles, whether you used left-hand cornered rectangles or right-hand cornered rectangles or midpoint rectangles, it did not matter. I mean, you got different answers until you got to the point where you made the rectangles so skinny that the width of the rectangle was almost insignificant. And so to find the area under y equals f of x, we add the areas of a bunch of rectangles. All right, so there's a lot of notation that went along with this. This idea of taking this region, taking the segment from A to B, breaking it up into small intervals, and then creating rectangles above those small intervals, finding the areas of each of those rectangles. The notation that went along with that was that we had the height times the width of each rectangle, where the width was delta x, and the height of that rectangle was the height of the function.
It's just Riemann sum, right?
That's right. So we take that height times the width, we add up all of those areas. So we have the sigma out in front, the sum where I goes from 1 up to n, where we had n rectangles, and this was an example of a Riemann sum. And then if we wanted to make a better and better approximation, then what we wanted to do is to have more and more of these rectangles and make the delta x get really tiny, which means that we're going to have more and more and more rectangles. So we're going to take a limit as n approaches infinity. And once we did that, then we ended up with the definite integral, the integral from a to b of f of x dx. So in terms of this notation, the f of xi is the height of your rectangle, the delta x is the width. The sigma notation in the front says add those areas of the rectangles up, and while you're doing that, make those rectangles really skinny. So that's our limit in the front. Now, what's weird about this is that once you put that limit symbol in front, then you can say that this Riemann sum is equal to this definite integral from a to b of f of x dx. And what I see over here is sort of the remnants of the notation from this Riemann sum. So over here I see this dx, which is still the width. It's just the width of a very, very, very skinny rectangle. And this f of x, well, that is still of the rectangle. And this S in the front, well, that's our integration sign, but it also tells us we're going to sum up, or we're going to add up all of the heights times our width. So we're going to add up the areas of our very skinny rectangles. Okay, so my point in talking about this is that when we're talking about a definite integral, I'm still thinking of this definite integral as height of a rectangle times the width of the rectangle, f of x, times dx, being our width, and then adding up all of those pieces. So I still want to imagine this picture that's going on here. And the thing that's really cool about this is that because when we have a function that's all curvy, I don't know a formula for the area under y equals f of x. Just, I mean, it's not, a rectangle or a triangle or something that I have a known formula for. But I can break it up into these rectangles, and over this little interval, my function is constant. So I can think of it as a sum of a bunch of rectangles, and I really do like rectangles because we know what the areas of those are. Okay, any questions about this idea that we haven't really been talking much about in this class, but you talked about it at the end of Calc 1? Okay, maybe I'll add one more comment here is that I'm going to put in quotes, find the area under y equals f of x, because technically when this function dips below the x-axis, then we talk about negative values. So area under really means area under f of x and above the x-axis. So when our function dips below the x-axis, then we talk about a negative value for this integral. Slightly different picture. Here's our y equals f of x. And then I'm going to throw in a second function, which I'm going to call y equals g of x. And so the idea is that we would like to be able to find the area below f of x, but above g of x. So what's crazy now is that not only do we have a curve as the ceiling of our area, of our shape that we're looking at, but now the bottom of our shape is also kind of funky.
So you can just decide to draw the outer line for everyone.
Well, this is just an arbitrary example right now. So, I mean, an actual example, then, yes, we're going to actually have specific values of this. Okay, so suppose that we want to find the area of the shaded region. Now again, this shaded region that we have here is not a shape that I have a known formula for, which means that we're going to have to integrate. And the reason that we integrate, and the reason that we talk about integration, is because we can take some funky shape, break it up into small pieces, like rectangles, that we can talk about the areas of, and then add all of those up. Okay, so if I do that over here, if I look at this region and I try and break this region up into rectangles, well, the rectangles are going to look something like this. Here is one of them drawn into the picture. Now there's a ton more of these. I have rectangles all the way along, and I'm not going to draw every single one. I'm just going to draw a couple of them. Here they are. And if I break this entire region up into rectangles, I have rectangles all the way over here at an x value of a. Rectangle, 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 rectangle. Keep going until I get all the way to b. And then the idea is that I'm going to find the area of each individual rectangle, add them all up. It'll give me the area of my entire region. Okay, so we'll add up the areas of a bunch of rectangles. Alright, so I'm going to focus on a generic rectangle right here in the middle. In fact, I'm just going to focus on the one that I drew first. I'll make that one extra dark. And so for this particular rectangle right here, the area of that rectangle is base times height. And so our base, well, I think of that as a change in x. It's a little bit along the x direction. Now, in terms of a Riemann sum, that's a delta x, but once I allow the number of rectangles to go to infinity, then that becomes a dx. And so I'm going to think of this little width here along the x direction as a width of dx. And then the height of this rectangle, well, that height comes from taking the top value on that rectangle minus the bottom value on that rectangle. And so the width of each rectangle is dx, and the height is going to be the top value on the rectangle minus the bottom value. Which, in this case, on this rectangle, that top rectangle is sitting on our top function. And our top function in this case is f of x. And the bottom of this rectangle is sitting on this bottom function, on the g of x function. So the width of one rectangle is dx. The height is f of x minus g of x. And so our area is going to be to take the area of one rectangle, f of x minus g of x times dx, and then do that exact same thing for every single rectangle, figure out all those areas, add them all up, starting at an x value of a and ending at an x value of b. Alright, so let's take a look at a real example. Alright, so we are going to find the area of the region bounded by y equals the square root of x, y equals 1 over x plus 5, x is equal to 1, and x is equal to 4. Alright, so the very first thing that we want to do is get an idea of what the heck this region looks like, which means that you want to make liberal use of your calculator. So if you have your calculator, please pull it out. And on your calculator, you're not going to be able to graph x equals 1 and x equals 4 because those are going to be vertical lines. But you can graph y equals the square root of x, and you can graph y equals 1 over x plus 5. So while you're working on those graphs, I'm going to go ahead and graph x equals 1. I know that that's a vertical line. And x equals 4 is also a vertical line. So as you're graphing the function y equals the square root of x and y equals 1 over x plus 5, in terms of the window that you look at, you definitely want to make sure that your x values include x equals 1 and x equals 4, and anything outside of that maybe doesn't matter so much. square root of x, which starts here at the origin, kind of pops up. So this is our y equals the square root of x. And then we also have y is equal to 1 over x plus 5. It kind of pops down along like this. Okay. Does everybody have a picture that looks similar to that on their calculator? Cool. Okay. So here's our picture, and so now we get to do the kindergarten part, which is some coloring. And so something to be a little bit careful of, and I do want to warn you this because this will happen to you at least once when you're working on these problems. There are several regions here that you could color in. I mean, I can color in this little section down here or this little section over here, but what you want to color in is the region that is bounded specifically by the 4 curves that are given to us. So in this case, we want the area below 1 over x plus 5, above square root of x, and between x equals 1 and x is equal to 4. And you may say, Diane, you're being silly. Why are you telling us that? That is definitely the region we want, but more than one time I have tried to color this region down below if I wasn't thinking carefully about what I was doing. Or maybe colored in this little triangle here. Maybe I didn't do that. That might be a little too silly. But I might color that region down below. Okay, so this is the region that we're looking at. So step number 1 is to understand what the picture looks like. Are there any questions about that picture? Okay. All right, so now we want to find the area of this region, and so our area is going to be all about taking the height of the rectangle times the width of a rectangle, and then adding up all of those areas starting at A and ending at B. So I'm going to start by drawing a generic rectangle somewhere in the middle here, and I want to get in the habit of doing this in every problem, because the idea of an integral is that we're taking a big blob that has funny sides on it, breaking it into rectangles or some other small shape, and analyzing that shape, and then applying that all the way along this blobby region. Okay? So I want to focus on one little shape that I'm going to be working with. So again, I do want to imagine rectangles broken up all the way along here, but I'm going to draw just one sort of generic rectangle that I'm going to analyze. Okay, so that rectangle that I have here, the width of my rectangle is a little bit of the x direction. It's a change in x, and so my width will be dx. And my height, the height of this rectangle, well, whether I've drawn this rectangle in the middle, or whether I've drawn this rectangle all the way on the left side or all the way on the right side, that top of that rectangle is always touching the red function. And so my height is going to be my top function, 1 over x plus 5, minus, well, the bottom of that rectangle is touching the blue function. And whether I have this rectangle drawn in the middle, or whether I imagine the rectangle drawn all the way over here to the right, that bottom of the rectangle is always on y equals the square root of x. Okay, so my area is going to be the height of my function, or the height of my rectangle times the width of my rectangle. That's the area of one rectangle, and then we want to add them all up. And so my area integral is going to look like 1 over x plus 5 minus the square root of x times dx. That's my height times my width. And I'm going to add up all of those areas. That's my integral sign. Starting at an x value of 1. And bam, 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 I'm going to add those areas until I hit an x value of 4. So my bounds will be from 1 to 4. Okay, are there any questions about setting up that integral? And this may sound silly that I'm setting this up and saying, and being very specific about the width and the height, but this is going to be really important as we work through this chapter. Every section, the theme is going to be break the object up into small pieces, analyze those small pieces, and then add them all up.
So your boundaries is just always your x values?
Yes, so your boundaries are going to be, in this case, because we have vertical walls, that's where we're going to start and end. And because our variable over here is an x, these boundaries are going to be x values as well. Okay, so now we've set up this integral, let's actually do some calculations here and figure out what the area of this region is. So the very first thing I might do is look at the integrand and see if I can clean this up at all. The setup is fine, but before I integrate, I want to clean this up. So I can get rid of these parentheses here. They're not really doing anything. Something else I can do is rewrite the square root of x as x to the 1/2. So we've got the integral from 1 to 4 of 1 over x plus 5 minus x to the 1/2. And then the dx at the end. And now comes the first section of Calc 2, which is we want to analyze this antiderivative. So the antiderivative of 1 over x, that's our natural log of the absolute value of x. And then we've got plus 5x. And now we're going to add 1 to the power. So we've got x to the 3/2 and divide by that new power, which, if you clean it up, becomes 2/3. We're going to evaluate this between 1 and 4. Okay, any questions about the antiderivative? Okay, so now it's a matter of plugging in some numbers. We've got the natural log of the absolute value of 4 plus 5 times 4 minus 2/3 times 4 to the 3/2. Minus, plugging in 1. And so when we plug in 1, we have the natural log of 1, which is 0. Plus 5 times 1. Minus 2/3 times 1 to the 3/2. Alright, so I guess technically this is a legitimate final answer. I mean, you entirely are in terms of numbers. So I guess you could call this a final answer. But it's not really satisfying, right? I mean, this really doesn't tell us anything about the area of that shaded region. So if you were to type this into your calculator, you should maybe double check and see that you get something approximately close to 11.72. And that would be square units. Okay, any questions or comments?
When we're going through and you ask us to actually evaluate it, are we going to have like our calculators for use, or are you going to set it up in a way that we can actually figure it out? Like, for example, like I don't know the natural log of 4 off the top of my head.
Right. So once you get to something like natural log of 4, absolutely, you know, figuring out your final. So on this example, let's find the area bounded by y is equal to 3x minus x squared, y is equal to 1/2 x squared, x is equal to 0, and x is equal to 3. Okay, so the very first thing once you write the question down or the problem down, is to say, okay, what the heck does this thing look like? Which means that you want to graph y equals 3x minus x squared, and you want to graph y equals 1/2 x squared. Now, for the sake of time, I'm going to go ahead and draw these functions. Okay, but you should double check and make sure that you agree with my picture. And so the blue function here is y equals 1/2 x squared. It's a parabola, touches at the origin. And y equals 3x minus x squared is also a parabola, but this parabola is upside down. And so this parabola is our pink one, which is y is equal to 3x minus x squared. Now there are some things that you might notice in your calculator, and that is that you might observe that the two functions look like they both cross the origin. And the other place where the two functions cross occurs before x equals 3. And so x equal to 3 is a vertical line. Oops, I didn't think I would curve quite long enough. X equal to 3 is a vertical line over here that occurs past the other intersection point. Okay, so we want to find the area bounded by y equals 3x minus x squared, y equals 1/2 x squared, x equals 0, and x equals 3. So when I look at these, what I actually see here are two separate regions. Okay? I've got this sort of almond-shaped region. And then I also have this kind of triangular region over here on the side. And so I actually have two separate regions. Now, I don't really know where this point of intersection is here right in the middle. So I'm going to put a question mark there. But as I start to think about these regions, and I start to say, okay, I want to find the area of these two regions, I say, okay, I'm going to break these regions up into rectangles. So I draw a random arbitrary rectangle, and here it is. Now, when I look at this rectangle, what I notice is that the width of that rectangle is a little bit in the x direction. It's a little portion of the x-axis. So my width is dx. The top of my rectangle is on the pink function. The bottom's on the blue function. Now, if you decided to draw your random rectangle over here in this other section, your width is still dx. But that height has now changed because the top of this rectangle over here is on the blue and the bottom is on the pink. And so these guys have flip-flopped right here at the intersection point. And what that means is because we have to describe these two rectangles in a different way, we have to set up two separate integrals. So because these two rectangles have different descriptions of their tops and bottoms, we must set up two integrals. Area is going to be equal to, the total area will be equal to the area of region A, which I'll call this region here, plus the area of region B. All right, so our setup for this first region, are there any questions about identifying that?
So we first have to graph every point to make sure that we know what the looks like.
That's exactly right. So every time that you have a list of equations, you want to graph it and understand what the picture looks like. So that is step number one every time.
So you see that it's broken up at that point where the question mark is. Will
Yes.
you ever have like two functions that like oscillate in such a way that you had a ton of points where the two are swapping and then you have to break it up into like a ton of different integrals?
That could definitely happen, but what you would hope would happen there is that they're oscillating in such a way that you have some symmetry, so that maybe this region and the other region were the same shape, so you just have to multiply times 2.
Actually figured out the question mark though,
So how would you figure out that question mark?
by putting the equations equal to each other.
Okay, so yeah, it would be really nice to know what this question mark is. So I'm going to put that question on pause here for a second, and we'll come right back to that in just a second. Okay, so thinking about that question mark, we do need to know that. And the way we're going to figure out is we're going to set those two functions equal to each other and solve for x. But we'll come back to that in just a second. I want to finish up talking about these rectangles that we have here. So these rectangles here, the first rectangle has a height of top minus bottom, which in this case the top is the pink function, so it's 3x minus x squared, minus the bottom of this rectangle, which is the blue function, which is 1/2 x squared. So that's the height of our rectangle. The width is dx. And we want to add up all of those rectangles. Now, in this first region, it looks like these two functions meet up right here at x equals 0. And so we're going to start at an x value of x equals 0, and we're going to go to the question mark. And Will's going to help us out with that question mark in a minute here. But for now, I've just got a question mark up there. Are there any questions about this setup? Okay? So we now want to add that on to the area of region B. Now, the thing that's different, the width is still dx. Our height, we're going to flip-flop our top and our bottom. And so our top function now is the blue one, which is 1/2 x squared, and the bottom function is the pink one, which is 3x minus x squared. And then we have our width, which is dx. So we've got our height, which is top minus bottom, and our width, which is dx. And we want to add up all of those rectangles, starting at that intersection point, which I don't know what the x value is just yet, and ending at x equals 3, because that was what we were told was our right-hand wall. Okay, any questions about that setup? So we need two separate integrals. So yeah, now we need to actually figure out what that question mark should be, and there's two options. One option is the algebraic route. So to find our question mark, well, it's the intersection of these two curves, so we can set those two curves equal to each other. And so we've got 3x minus x squared is equal to 1/2 x squared. And so that would give me 3x minus 3/2 x squared if I move everything to one side. And because I do have x squared terms, I do want to actually factor this thing. So I want to move everything to one side. Okay. And now I can factor out, what can I factor out here? Yeah, I can definitely factor out an x. And so I've got 3 minus 3/2 x equals 0. So I've got x times 3 minus 3/2 x equals 0. Now, what's nice here is that either x equals 0 or 3 minus 3/2 x is equal to 0. And this x equals 0, that totally makes sense because that's right here at the origin. That's where our first intersection was. And the other one, I've got 3 is equal to 3/2 x, multiply both sides by 2/3. And so we end up with x is equal to 2. And so this question mark here, rather than being put on pause now, is an x value of 2. So now I can go back to my integrals up here and cross off my question mark and replace those with 2's. All right, any questions about that? So I do need to know those intersection points. One option is the algebraic route, set those two functions equal to each other and solve for x. The other option is, in your calculator, if you have these two functions graphed, then you can calculate that intersection point via the intersection function on your calculator. So both methods work and both methods are fine. All right. So I know I've kept you over our 50-minute, but I do want to wrap this question up. And so the very next step on this one is that we would have two integrals. We'd simplify both of them, and then we'd integrate. The only catch that you need to be really careful about is when you're subtracting, because we're always subtracting these problems, a top minus a bottom, if that bottom function is more complicated, such as 3x minus x squared, make sure you have those parentheses. And in the cleanup phase, distribute that negative sign. So your next line is going to look something like this. So your area will be the integral from 0 to 2 of 3x minus x squared minus 1/2 x squared gives us minus 3/2 x squared dx plus our other integral is from 2 to 3. And when I look over here, I need to remember to distribute this negative sign. So I've got 1/2 x squared plus an x squared gives me a positive 3/2 x squared minus 3x. And then a dx at the end. And so now there's a bunch of calculus and integrating that goes on here and plugging in of boundaries. And in your final answer, and you should check this first integral comes up to be a value of 2 square units. And your second integral also comes up to be a value of 2 square units. And you should check both of these. So our final answer is that the area of the region that we're interested in is 4 square units. All right, are there any questions about that? Questions about this? It is crucial to understand what the picture looks like.
So all you did, you still got to do the evaluation, right? 2 minus 0 and then plus the 3 minus 3.
That's right. So you still first got to take your antiderivative and then plug in your boundaries. That's in the ...
Okay.
Jeff?
When I first looked at this, it just seemed like we were taking the area under the curve on the first one and then subtracting the area under the curve from the second one.
Yes. So one way that you can that's an alternate way of thinking about this is thinking about this as the entire shape. Area under the pink one minus the area under the
We
blue
just
one.
don't go through the process of doing that by combining the formulas.
Right, and in
And then
fact,
it's just the height.
you would still have to break it here at x equals 2.
Right.
But you could certainly set this up as area under the pink function minus the area under the blue function. It would be the same, that would be conceptually equivalent to distributing the integral sign right up here.
Right.
So, and the reason that and absolutely that's a valid way to think about it, but I'm going with the think about the little piece because it's sort of the theme that's going to happen.
Like say like on this one, like we do all the math right down to there, but the calculator comes, we just don't do right on the calculator. We get most of the points, right?
So there's two major ideas that are going on here. One is the setup of the problem. And in terms of finding the areas, that's going to be the biggest part of the actual question, is have you set it up correctly? And then from there, did you calculate the integral correctly is a small portion of the problem. Okay, other questions? Okay, so let's stop here. Please take a 10-minute break. When you come here, our job is to find the area bounded by x is equal to 1 minus y squared and x is equal to y squared minus 1.
So you solve for y in one, plug it in the other?
What's that?
Or you solve for y in one, plug it in the other?
All right, so the question now becomes, okay, find the area bounded by these guys. And so we want to know what these equations look like when we graph them. Now, because they're written as x is equal to stuff in terms of y, that means that you can't graph that on your calculator unless you do something such as, and so if I take one of these, here's my thought bubble over here, x is equal to y squared minus 1, and I solve for y.
X plus y.
So, yeah, when I solve for y here and I move stuff over, I've got y squared is equal to x plus 1. And when I do this, then when I take my square root and solve for y, I have plus or minus the square root of x plus 1. Okay. And so I actually now would need to graph both y equals the positive square root of x plus 1 and y equals the negative square root of x plus 1. So I'm showing you this as an option, but this is not what I would recommend. What I would recommend on this problem is that we've got equations that are not too terrible to deal with. Okay? For example, this x equals y squared minus 1. If I cover up the minus 1, that looks an awful lot like a parabola. It's just a parabola that's opening up to the right instead of upwards. And this minus 1 says that I'm going to shift 1 unit back on the x-axis. So this one right here, if I have some knowledge about parabolas, then x equals y squared minus 1 is a parabola that opens up to the right. Now this other one here, x is equal to 1 minus y squared. If I cover up that 1 for a minute, x equals negative y squared is going to be a parabola that opens up to the left, to the negative x direction. And that adding on the 1, if this is negative y squared plus 1 is another way to write this, then I'm taking this parabola that's opening up to the left, and I'm moving it 1 unit in the positive x direction. And so my parabola is going to open up to the left. It's going to look something like this. So we have x is equal to 1 minus y squared. And again, yes?
Couldn't you just graph it pretending the y squared is x and then just turn it on its side?
Sure, absolutely. Another way to think about that is flip-flop the x's and y's and then reflect it across the y equals x diagonal line. There's another way to think about that.
Well, why don't you recommend just
So the reason that I don't, it's a valid way to go about the problem. The reason that I recommend this other option, these are supposed to be symmetrical, left and right side are supposed to be the same shape. The reason that I recommend working with these shapes is that these give you a little more sense of, okay, this really is a parabola, and when you graph this, sometimes your calculator doesn't always give you a picture that's quite as nice as what you'd be looking for. Maybe on this particular example it does, but in general, if you can understand the inherent nature of what's going on with these without solving and getting plus or minus square roots and stuff, then it's a better option.
Just as if you just exchange the x's and y's, would the area still be, would it be the same?
So if we exchange the x's and the y's,
So you'd have y equals 1 minus x squared?
Sure.
It'd just be over the x-axis.
That's
up
right,
and
we'd have
down.
an up and down shape.
Would the area be the same?
The area should be the same.
I would think so, yeah.
And maybe, and if you want to convince yourself, you might reset up
Right.
the problem and see what you come up with in the end. But the area should be the same. Okay, so there's lots of ways to deal with this funkiness, with this sideways picture. One is to essentially do a variable swap and redraw the picture. I'm going to stick with the variables as they are, the pictures as they are, because we may or may not always be able to mess around with the picture and flip it on up into a vertical direction. Okay, so I'm going to stick with this one as it is. So this is our picture. So here we have our picture. We'd like to find the area of this kind of flat football shape that's going on here. And so if I start by drawing a rectangle, then the rectangle that I draw, if I draw it over here on this left-hand side, I run into a problem. Because what I notice is that the top of my rectangle and the bottom of my rectangle are both lying on the same curve. And that's a problem. So instead of thinking about a vertical rectangle, what I might do is take rectangles that are horizontal. And notice that if I have a horizontal rectangle, one side of my rectangle is on the blue curve and the other side is on the pink curve. And whether I draw that arbitrary rectangle kind of up higher or down lower, always the left side is on the blue curve and the right side is on the red curve. Okay. So now I have a picture where my top and bottom of my rectangle are touching different functions, and this is a good thing. Or different curves. Okay, so what this means though is that we're going to need to make some adjustments. So vertical rectangles don't work well because the top and bottom of the rectangle will touch the same curve. So we'll use horizontal rectangles. All right, so here I want to analyze the one rectangle that I have. And in terms of this rectangle, we've got length times width. Now I'm going to start, and I always want to start by looking at the skinny side of the rectangle. Now in this case, the skinny side of our rectangle is a little bit of the y-axis, so it's a delta y, or if we look at an integral, dy. So the width of one of our rectangles is dy. And the height of this rectangle is going to be top minus bottom. But that's a little weird because our top minus bottom is now sideways. So think about when we talk about top minus bottom on the y-axis, top is the larger y value, bottom is the smaller y value. So when we turn sideways, larger is toward the right side. And so the top of this rectangle is the side that has larger x values. So in this case, our top side is the pink curve. So our height is pink minus blue, which in this case is going to be 1 minus y squared minus y squared minus 1. Now, there's something that I wrote down here that's a little bit strange. Notice that I wrote down, I had x is equal to 1 minus y squared, and I actually wrote down the 1 minus y squared as my top, my rightmost side of the rectangle. This y is important because my variable for my width and the variables that show up in my height must match. Okay? So I have a note to myself, dy, everything down here must also be in terms of y's. Okay, so now we want to set up our integral. So our area will be our height, which is 1 minus y squared minus y squared minus 1 times the width, which is dy, and we want to add up all of those rectangles. Now, when I'm thinking about adding up these rectangles that I have here, what I'm thinking about is, okay, I've got a bunch of these rectangles, I could draw them all out. The lowest rectangle occurs down here at this intersection point, and the top rectangle occurs at this top intersection point. Now, because we have everything in terms of y, our boundary values are also going to have to be y values. And so now I need to figure out what these intersection points are. I can look at this and say, okay, yeah, they're probably y equals -1 and y equals +1, but if I didn't know that, then to calculate my intersection points, I can take my two equations and set them equal to each other. And so we've got 1 minus y squared is equal to y squared minus 1. And so if I add 1 to both sides, then I've got 2 minus y squared equals y squared. Move the y squared over to the right side. And we've got 2 is equal to 2y squared. Divide both sides by 2. We've got y squared equals 1. And so when you take your square root of that, you get plus or minus 1. And so our bottom y value down here is y equals -1. And our top y value is y is equal to 1. And so we're going to start adding up rectangles at y equals -1 and stop adding up rectangles when y is equal to 1. Okay, are there any questions about setting up this integral for area? The big deal is that sometimes a vertical rectangle might not make sense to draw, and the reason is because when you have a rectangle, the top and the bottom are on the same curve. It doesn't work out so well.
So if you swapped those two things and
Yes.
then you swapped your boundaries, would you get the same answer?
You would, yes. Because swapping inside here gives you a negative, and then swapping the boundaries also gives you a negative.
So as long as you are subtracting in a way that you are following your limits of integration.
Yes. Okay, other questions? Okay, so if I wanted to continue with this problem, once I have this set up, my next job is to simplify. So inside of my integrand, the setup 95% of the time means once we've set it up, we need to do some simplifying, distribute the negative sign, and combine some terms. And so we end up with 2 minus 2y squared dy. Your next job is to find the antiderivative, plug in the boundaries. So our antiderivative is 2y minus 2/3 y cubed, evaluated between -1 and 1. Then you have to plug in those boundaries, simplify some stuff, and you should check, once you do all of that, that you end up with 8/3 as a final value. Okay, are there any questions about that? Okay.
Usually, the area below the x-axis is negative, but in this problem it's not, right?
That's exactly right. So when we talk about, so that idea of area below the x-axis being negative, it actually comes from, so let's say that this is our function y equals f of x. Because technically, when you are looking at the integral of f of x dx, then from a to b, then what you're really doing is top minus bottom, but then here your top gets inverted. So this is really f of x minus 0, and then we would continue on here with f of x minus 0, which is why this value becomes negative. But what we're doing is we are consciously making an effort to switch our top and bottom for places where something like that happens. Yeah, so always, 100% of the time, when we're talking about area bounded between curves, that area will be a positive area, whether it's located here, whether it's located up here, down below the x-axis, wherever. Okay, other questions? All right. So in that case, what I'd like to do with our last 20 minutes of class today is give you an opportunity